Hey guys, we're looking at another method to evaluate limits. Let's see, for Calc BC, we began the year looking at limits and how to evaluate limits. And, I guess that was the same for Calc AB as well. We kind of did limits at the beginning of the year. But here's how we evaluated limits. We had basically plan A, plan B, plan C, plan D/E. So plan A, we always use direct substitution. So we take whatever the limit as x approaches whatever. We take that number, we sub it into our function, we cross our fingers, and we hope we don't blow up. We usually blew up. Direct substitution almost never works. You know that. So our next step was to try to factor, cancel, any kind of algebra simplification. If that didn't work, we tried to rationalize the numerator. If that didn't work, we tried to maybe graph it and see where it went, or use a table of values, like plug in numbers super close to the number that we're approaching. So now that you are like experts at derivatives and things like that, I can show you a plan. I call it A and a half because it's really between plan A and plan B. But it only works when you get something called an indeterminate form. So we're going to use direct substitution. We're going to sub in our number. And if what we get is an indeterminate form, I'll show you what those are in just a minute. We're going to use this guy's rule that he made up. And it looks like El Hospital, but it's pronounced L'Hôpital. So we're going to use L'Hôpital's rule. Now let me go back and show you what an indeterminate form is. These are on the very last page of your notes. There are 7 different types of indeterminate forms. In Calc AB, the only types of indeterminate forms that we encountered were if we plug in, if we sub in a number, we end up getting 0 over 0. That was an indeterminate form. It happened kind of frequently. And then also sub in a number, do your limits, and you get infinity over infinity. Those were the only 2 types of indeterminate forms that we saw in Calc AB. The ones that you'll see in BC might be where you are subtracting 2 functions, so you do the limit on this one and the limit on this one, you end up getting infinity minus infinity. Well, this is an indeterminate form. You don't know what levels of infinity these are. They're not necessarily the same value, so you can't say that this minus this is 0. 0 times infinity. I know this is kind of hard to wrap your brain around. You're like, why is that an indeterminate form? 0 times anything is 0. Well, keep in mind, when you're doing a limit, you can say the answer to your limit, the answer to this particular limit is 0, but that doesn't mean your values are 0. You're just getting values that are super tiny. When you take those super tiny values that are close to 0, and you times it by some infinitely large number, you have no guarantee that this always heads towards 0. Okay? 0 to the 0 is an indeterminate form. Remember, these aren't really zeros. We're doing the limit on this and raising it to this power that isn't really 0. These are close to 0. It's something super tiny, maybe to a super tiny power. And then 1 to the infinity. Most people would be like, come on, you take 1 times 1, you take 1 times itself over and over and over again, your answer is not going to change. Right. But we don't know. This isn't necessarily 1. It's the answer to our limit. These are just numbers close to 1. And we're multiplying it by itself over and over and over again. We have no guarantee of where that's headed. Okay? And same concept here. So, these are your 7 indeterminate forms. And, you can kind of compare, of course, 0 over 0, infinity over infinity, infinity minus infinity. You cannot tell what that is. However, you do know if you have a positive infinity and you're adding it to more positive infinity, you know where that one's headed. This is not an indeterminate form. if they're both negative. Basically, you're combining two large negatives. That's headed to negative infinity. You know that. Oh, yeah. See? I had to think about this one for a minute. 0 to the infinity power. Okay, so remember, when we're evaluating limits, we don't know that this is 0. It's something close to 0. Well, how do you know? How do you know this is 0, but that's not? Well, think about this. This is a number close to 0. It's like a fraction or a decimal close to 0. When you take that tiny number and you multiply it by itself over and over and over again, tiny decimal times same tiny decimal times same tiny decimal, your values keep shrinking and shrinking and shrinking and shrinking, and that is headed towards 0. We know where this one's headed. We don't know where these are headed. Okay? So, kind of hate to tell you this, but BC students, you need to memorize those 7 forms. You need to memorize these 7 indeterminate forms. This is, when you get one of these by direct substitution, that's like your permission slip to use L'Hopital's rule to find the derivative. So memorize those 7 indeterminate forms. Okay, here we go. Let's go ahead and start doing some problems together. So here I go. I'm going to sub in 1. And I get natural log of 1 over 1 minus 1, which is 0 over 0. This is an indeterminate form, which means I can use L'Hopital's rule. Now, let me show you what L'Hopital's rule is. Oh, I forgot to tell you what L'Hopital's rule is. So L'Hopital's rule says, all right, you're trying to do a limit, and we're doing a limit on fractions, okay? So most of our indeterminate forms involve or can involve a fraction. What we're trying to do is we're trying to say, how about, where are these y values headed? Where are these y values headed? Let's compare these y's to these y's. And you can't. Because maybe these are headed towards 0 and these are headed towards 0, and oh my gosh, you have an indeterminate form. If you can't get the answer to the limit by comparing these y values, what you can do is you can find the slope of this function, and you can find the slope of this function, right? And whatever the y values would have been when you're trying to compare them, their slopes make that same comparison. So we're doing rate of change on this function, we're doing rate of change on this function, and then we're finding out, as x approaches a, where is this one's slope headed, where is this one's slope headed? And we'll compare slope of this one to slope of this one and say, ah, there's my answer. Okay, so we're going to do limit as x approaches 1, and if this is f of x, I want to do the derivative on f of x. And if this were g of x, I want to do the derivative on g of x. This one's slopes and this one's slopes are actually headed toward each other. That's why I get the 1 over 1. They're actually headed toward 1, and when you compare those, you just get 1. This is kind of dangerous. Teaching you L'Hopital's rule, I hope that it's far enough away from back when you did quotient rule, because what kind of scares me is when you need to do a derivative on a fraction, you can't take the derivative of the top and the derivative of the bottom. If your goal is to take a derivative on a fraction, you can't do that. You have to use quotient rule. However, when you're evaluating a limit and you get an indeterminate form. L'Hopital's rule says, look at the derivative of the top one, look at the derivative of the bottom one, and see where their y's are headed. Okay, something else I want to point out, and I've just learned this summer. So when I was doing AP grading, I started out grading AB exams, and then we finished. We finished early, so my leader of my group session said, hey, let's start grading some BC exams. So I got to grade some BC exams as well. One of the questions on one of the BC exams was L'Hopital's rule. Here's what I learned. In all of my little definition boxes, I said you can use L'Hopital's rule if the limit of this over this equals 0 over 0. If the limit of this over this equals infinity over infinity. Turns out we're not allowed to say that it equals 0 over 0. It's not a thing. So I can say the limit of something something equals infinity. This is a location. It tells me where my y's are headed. I can say that my limit equals 0. So it's a value. It's where my y's are headed. I can't say that this is where a function is headed. A function can't head toward 0 over 0. It can't equal that. So if you notice, on all of these indeterminate forms, there's a space here. You know why? I whited out the equal sign. We're not supposed to say that when I sub in my numbers, it equals this over this. This isn't a thing that we can equal something to. This isn't a thing that we can equal something to. Neither is this. Neither is this. We can't say that it equals this. We can write this on our paper, but don't say that this equals. This isn't something I can say it equals. Can't say it equals. So notice up here when I wrote, I can say this limit does equal this, because I subbed in 1. It does. It does equal this. But I can't write that it's equal to this. This is supposed to be on your paper somewhere because you're supposed to prove that you know you have an indeterminate form, but just don't say ever that it equals your indeterminate form. Just be careful with your equal sign. Your answer could be totally right, but they're going to look back up and say, ooh, did the student ever say that it equals the indeterminate form? And if you do, you get like a point taken off for that. Weird. Blew me away. Had no idea that they were going to be so picky on something like that. Okay, moving on. Sub in infinity. So I get e to the infinity, which is infinity, over infinity squared, which is infinity. This is an indeterminate form. Notice I didn't put equals in front of it. So since it's an indeterminate form, we have permission to use L'Hopital's rule. So again, still doing a limit. Derivative of the top function, derivative of the bottom function. E to the infinity is infinity. 2 times infinity is a different infinity. Well, dang, there's another indeterminate form. But I think you can see that our denominators keep knocking down 1. So let's try his rule again. E to the infinity is an infinity over 2, which is still just infinity. And that is an acceptable answer for a limit. So what we're saying is the y values of this function are headed toward infinity. Next one. Natural log of infinity. Okay, if you know what your natural log graph looks like, and golly, I sure hope you do. Natural log graph looks like this. And it does continue to grow slowly, but it does grow. So the top is headed toward infinity. The cube root of infinity, that's headed toward infinity. So that's an indeterminate form. Oh golly. Dang. X to the 1/3. X to the 1/3 is 1/3 x to the negative 2/3. Okay, so the one, it's I got 1 over x divided by, so I can do same change flip on that one. I can do same change flip on that one. And basically I get limit of 3. And that's x to the negative 1/3. X to the negative, yeah. So, this ends up being 3 over infinity. So 3 divided by huge equals 0. Whew, next one's a fun one. Sub in 0, so I get tangent of 0, 0. 0 minus 0, 0, 0. Definitely we get an indeterminate form. So we're going to use L'Hopital's rule. Here I go. Derivative of the top. Derivative of tangent is secant squared. Derivative of the bottom oh boy, next is 0. Well, secant is cosine upside down. So cosine of 0 is 1. Turn 1 upside down, you get 1. 1 minus 1. I think I see where this is headed. Over 3 times 0 squared. Got another indeterminate form. Let's use him again. Secant squared, I'm going to power rule, so I'm going to bring my 2 down in front. Same, lower it to the first. Chain rule. 2. Secant to the first times the derivative of secant. And I could simplify it, or I can just try it. I can cross my fingers and just really hope this is going to work. It's not. So this is obviously the denominator is going to be 0. I don't even have to do the math on these two because I know that tangent of 0 is 0. And because of this as being 0, it wipes out my entire numerator. But what I might want to do before doing another derivative is go ahead and simplify the top just a bit. So let's see. This is Yeah, I don't think anything cancels. I know sometimes when I have tangent and another trig function, they kind of cancel. These don't. This is 1 over cosine. This is sine over cosine. So like both my cosines would be on the bottom and nothing would cancel. I'm just going to keep it the way it is, but I'll call that 2 secant squared. Okay, not using L'Hopital right this minute. I'm just doing a quick rewrite on my limit. Secant squared. Okay, now let's use him again. Okay, I think I'll do product rule on the top, and I'll call this my 1 and I'll call this my 2. So 1 D2 2 D1 4. This is to the first. Now chain rule it. Okay, now let's see if we can sub in 0 without blowing up. Maybe, since our x is off the bottom, maybe it's going to work. Let's find out. Basically, 1, 2. 1d2 plus 2d1. Basically, I have 2 terms. I have this term, and I have this term. Well, this term has tangent in it. So I know that when I sub in 0 for my angle, these are wiped out, gone. So let's just focus on this one. And we already kind of talked about what secant of 0 is. So it's cosine of 0, which is 1, turned upside down, which is still 1. So I got 2 times 1 squared times 1 squared. So 2 times 1 is 2. So my numerator is 2. My denominator is still 6. Ooh, cool. I got a halfway decent answer on that. Alrighty, last one. Find the error in the teacher's work. Here I go. I'm just gonna just, how much do you trust me? So limit x approaches pi of derivative of sine is cosine. 0, derivative of cosine is negative sine. So that's getting close to -1. That's getting close to sine of pi. Well, it's a positive tiny. So maybe I could say that the answer to that is negative infinity. And actually, I got to be careful. It did say, and I wanted to make this a little bit easier, which makes it invalid. So there was a negative sign here, and I took it off because I didn't really want to deal with it. But because we're approaching pi from underneath it, That's why I can say that this is approaching a positive tiny. Anyway, the point of the whole problem is I made a mistake at the very beginning. So at the very beginning, I never even subbed in pi to determine if I had an indeterminate form. So if I go back up here to the beginning, if I look at, don't use this rule, sine of x. So as I approach pi from the left, oh gosh, these values are getting super close to 0. So positive tiny. And I'm not going to put equals, I'm just thinking out loud here, okay? And then 1 minus cosine. Well, as we approach pi from the left, let's look at our cosine graph. That's getting super close to -1. And here's the thing. So that's getting close to -1, 1 minus -1. So this is, again, this is close. This is getting close to 2, this is getting close to 0. And basically we get something basically we get kind of like 0 divided by 2, which is 0. Turns out the answer to this limit is 0. Not negative infinity. And I've kind of butchered it along the way, but my point was supposed to be make sure you have an indeterminate form before you jump in to using L'Hopital's rule. Okay? So if you can get the answer, go ahead and get the answer. If you get an indeterminate form, that's the only time you can use L'Hopital's rule. Sorry, that was kind of lame. Just to make the point, make sure you have permission to use L'Hopital's rule before just jumping into it. Okay, I'm done. Signing off here.